Good afternoon, everyone. It's a packed house. Welcome to the 2025 Harold Berger Award Lecture. I'm Vijay Kumar, the Dean of the School of Engineering and Applied Science, and I'm so honored to be here today. I present this award to Moungi Bawendi, the Lester Wolfe Professor of Chemistry at the Massachusetts Institute of Technology. Before we welcome Dr. Bawendi to the stage, I want to spend a few minutes talking about Harold Berger, the gentleman after which this lecture has been named. The late Harold Berger graduated from the Moore School, now part of Penn Engineering, with an electrical engineering degree in 1948. He later earned his JD at Penn Law in 1951. Judge Berger was a managing partner of Berger Montague, a prominent law firm in Philadelphia. Prior to that, he served as a judge of the Court of Common Pleas of Philadelphia and was the past chairman of the Federal Bar Association's National Committee on Federal and State Judiciary. He was the author of numerous law review articles and lectured extensively before bar associations and at universities. He was a permanent member of the Judicial Conference of the United States Court of Appeals for the Third Circuit and the chair of the Aerospace Law Committee of the American, Federal, and Inter-American Bar Associations. He was elected to the International Academy of Astronautics in Paris in recognition of the importance and impact of his scholarly work. One of our most prestigious alumni, Judge Berger, was also very active throughout his life in alumni affairs at Penn, both in the law school and in the engineering school. And here he served as the engineering board of advisor for many years, and his loyalty, generosity, and advice to the board is greatly appreciated. Judge Berger passed away on August 26th, 2023, at the age of 98. And we're so honored to be celebrating his legacy through this award. The Harold Berger Award was first established in 2002 to recognize technological innovators who have made lasting contributions to the quality of our lives. Its prestige is illustrated by previous recipients like Craig Venter, Dean Kamen, Thomas Check, and most recently Drew Weissman and Catalin Carrico. And of course, this is an illustrious club, but I can think of few individuals who are more deserving of this award than today's recipient, Dr. Moungi Bawendi. To introduce our awardee, I would like you to join me in welcoming to the stage Professor Christopher Murray, who is the Richard Perry University Professor in Materials Science in the School of Engineering and Applied Science and in the Department of Chemistry in Penn Arts and Sciences. Chris?
So good afternoon, folks, and it is truly an honor to have an opportunity to introduce Moungi G. Bawendi. Moungi began his interest in science very early with a rise in his studies through Harvard. He did his bachelor's degree at Harvard and then a master's, completing that in 1983. He went on to studies at the University of Chicago, eventually, as he shared with students today, following a line towards theory, and then came to love the possibility of getting his hands on the experiments and generating data, and he moved to doing high-resolution spectroscopy. But in that process, he had a deep love of understanding of quantum mechanics and the behavior of systems on multiple length scales. Summer internship at Bell Laboratories was an eye-opening experience where he had a chance to join at a very exciting time working with Louis Bruce, who he would also share a portion of the Nobel Prize with in the recent recognition. But that energized him to go on and complete his graduate studies, but then to go to Bell Labs as a postdoc during that period when things were really just exploding in terms of new understanding of what was possible with solid-state systems. And so I was lucky enough, along with Sherry Kagan and a few others in our community, but to be one of the first students to intersect his path as he started as a young professor in 1990 at MIT. His work through that time, rising through the ranks, ultimately achieving tenure and then full professorship, was recognized along the way with many awards. So things that we think of in terms of Packard Research Fellowship, Sloan Research, the Dreyfus Award for Early Investigators, and so on. But the recognition of that work and its impact on many areas surrounding chemistry, physical phenomena of optical materials, garnered additional awards in our field, the Ernst Orlando Prize, Lawrence Prize, also the Sackler Prize. But the impacts in terms of Moungi's work, I think, is through not only the science and the talent that he helped to develop, but also his broad curiosity in seeing that science translate into new opportunities for exploration in commercialization and new technologies. So I would like to invite Moungi Bawendi to come and share with us some of his insights today. Thank you very much.
Well, thank you, Chris. Thank you, everybody, for coming today. I've had a wonderful visit so far. It's a vibrant community. Research is incredible. Facilities are really amazing. And yeah, you guys are doing good work. What I'm going to tell you today is a story. It's like the origin story of quantum dots. So it's at a very high level through the technologies that spun out. So as Chris mentioned, I started out as a theorist doing statistical mechanics, and I became enamored with very small molecules, and the quantum mechanics of very small molecules. And so quantum mechanics really was something that I really loved. And the quantum world is such a strange world. Things are counterintuitive sometimes, or magical. I love teaching quantum mechanics. The first course I taught at MIT was graduate quantum mechanics. Did that for 7 years, and I'm teaching it again now, and it's just my favorite course to teach. I think it's just so amazing. And since this year is the 100th anniversary of the quantum year, this is a very appropriate time to talk about the incredible beauty of quantum mechanics and what it has done. We're surrounded by, without quantum mechanics, there wouldn't be life, right? So it's the stuff of life, right? But there wouldn't be chemistry, there would be no covalent bonds. Covalent bonds are there because of quantum mechanics. So it's incredibly important. So I'm going to tell you about quantum dots, which I'm sure all of you probably know something about. So what is a quantum dot? A quantum dot is simply a piece of semiconductor that's very small, nanometer size. But most importantly, if you put an electron in a quantum dot, then the properties of the electron are quantum mechanical. They're wave-like. And I'm going to tell you a little bit about that. So when you make quantum dots, as you know, they're very small, so you can't see them with a light microscope. And so for what I want to talk about is the importance of improvements in technology to drive science, right? So one of the technologies, which is obviously still around today and very important, that really helped this field of nanoscience get propelled in the late 70s, early 80s, et cetera, was electron microscopy. The ability to be able to see the structure of what we're actually studying, that was key to understanding the material itself. How do you know about polydispersity, whether you're making everything the same size if you can't actually see it? You can use small angle X-ray, it gives you an idea, but actually seeing the individual dots and looking at the different shapes, et cetera, that turned out to be critical to the advancement of the field, and it still is today. And so this is one of my students using an electron microscope, very much like the one that's in Chris's lab from a few years ago, maybe 10 years ago or so. And so, you don't need a very fancy microscope to see the quantum dots. And then when you take an image, you see these things. And this is, these are reasonably good quantum dots. And without having a picture like this, you don't really know what you're working with. And so it's very, it's foundational to be able to see something like this. So these are the quantum dots. They're about 4 nanometers, 5 nanometers in diameter here. These are cadmium selenide, so semiconductors can come as all one element like silicon, but most semiconductors are actually bimolecular, they take two elements. This has happened to be cadmium selenide here, which has turned out to be the hydrogen atom of quantum dots. Anytime we have a new idea of doing an experiment, we usually go to cad selenide because it's the most studied, in some ways the most robust system, and we can really begin to understand things. And then we move on to other semiconductors, indium phosphide or the 3,5s or ternary semiconductors to apply what we've learned to other systems. Okay, so that's the material itself. Let's talk about the quantum mechanics. And so I'm going to show you an experiment, and a video connected to that experiment, which I show it every year when I give my quantum mechanics class. And every time I look at it, I just my heart races. I love this video. And it's the concept, particle wave duality. We all know about that. It's important in quantum mechanics, but to actually see it in a macroscopic experiment, I think really brings the concept to life. And so in this experiment, this was done at Hitachi, not so long ago. This is from 1989. This is in an electron microscope. And there's a very, very thin filament here and two charge plates. And so the source, this is a source of electrons. It shoots out one electron at a time. Okay? One electron at a time. And this configuration here, it looks big on my screen here, but it's actually pretty small in the microscope. There are two identical paths for that electron to go through. So you know the Young's two-slit experiment. You've got two slits, and the light has two ways to go, right? So this is a little bit like that, but it's for electrons, right? So the thing that I find mind-boggling in this experiment, I'll go back to it, is that this is an experiment where you have one electron coming out as a particle, and then you detect that electron on a scintillator, and then eventually on a CCD camera, as a particle, right? The electron hits the scintillator, and you see where it hit it, right? But in between the source and the detector, that electron has wave-like properties, yeah? A wave that fills the entire apparatus, which is this macroscopic human-made apparatus that's on, it might be very thin, but it's still on the length scale of humans. Okay, so let's go ahead and do that experiment. Okay, so just as a reference, this is the setup, and there's the video. So now we start to see these electrons appearing sort of randomly on the scintillator. And if it were a classical system, you might think that this filament is going to act like a shadow, maybe, right? So sometimes the electrons will go this way, but maybe they'll never go straight down. And so we might see two blobs, with a vertical sort of shadow in between. Maybe this shadow is so faint that we'll just see random. So what you see here is sort of the statistical distribution of particles, right? Quantum mechanics has a lot to do with statistics. You do the experiment over and over and over again, and every time you get a slightly different result. So that's what we're doing here, right? Particle comes out, comes back. Okay, so now it's sped up a little bit. This whole experiment probably takes half an hour. But we're speeding it up, and as the experiment goes, you start to see that it's not actually random, right? You start to see a pattern, right? You see these stripes going down. So it's not a shadow with two blobs, it's an interference pattern. An interference pattern, just like the Young's two-slit experiment, where you have a wave coming in, get the two slits, and you create the interference pattern, which is just like the interference pattern we see here. That one electron, when it goes through the apparatus, it goes from being a particle, it interacts with this macroscopic apparatus as a wave. It's not that it chooses to go one side or the other, right? It's that wave that sees the entire thing, interferes with itself. I think the concept of an electron interfering with itself is just mind-boggling, right? But it turns out we use that concept all the time when we do interferometry, right? There are two arms in interferometer. with light, with photons, you think, okay, the photon goes down one arm or the other. It doesn't go like that. It goes through both arms at the same time. You've got this big wave function that interferes with itself. Usually you think of it as an electromagnetic wave, but actually it can work even with one photon at a time. So this is a really important concept. So this shows that an electron really is a wave. One electron, you don't need a beam of electrons. Just one electron is a wave. Okay, so why is that important for quantum dots? Because we're talking about a single electron in a particle that behaves like a wave, right? So, okay, electrons can be waves. All right, so if it's macroscopic, like the source of electrons, like in a wire, you know that it behaves like a particle carrying charge or energy, whatever. But if you were to take that same electron and putting in a nanobox, then that electron becomes like a wave. Just like an electron in a molecule, in a bond, it has wave function-like properties. It's not a particle. The same thing in a nanobox. This is the particle in a box, right? It's a wave. And our boxes are the quantum dots, right? So that's the quantum confinement. You confine the electron enough so that it no longer is whizzing around, but it's occupying the entire box coherently. The word coherent is really important, as a wave, as a state. Okay, so now the box becomes a cavity for that wave, right? And we know that cavities of waves give rise to their property. Like for sound waves, if you have a flute, big cavity compared to a piccolo, the tone of the flute is much lower pitched than the tone of the piccolo, right? So the cavity tells you what the energy of the sound is going to come out, or the frequency of the sound is come out. The same thing for organ pipes, right? So the little organ pipes have a higher pitch than the big organ pipes. So the cavity defines the sound or the pitch that comes out. Very similar to the quantum dot. So what is pitch for the quantum dot? It's energy, right? It's energy. So you create an electron, the small cavities will have electrons with higher energy, and the bigger cavities will have electrons with lower energy. Okay, so let's do that. So we've got a bunch of these quantum dots, different sizes. Right now they're full of electrons, but all these electrons are tied up right next to atoms. They're not these waves that I was just describing, right? They're part of the elements, right? So the first thing we need to do is to put in an electron in the cavity. How do we do that? Well, we could think of putting a circuit and putting an electron in there, or we could simply use light, right? We use light to liberate an electron from one of these that is closely tied to one of the atoms, to liberate it to fill the entire box. And how do we do that? We shine light on it. We shine blue light, we excite it, and we create that wave, that electron as a wave. And eventually, that electron that occupies the entire box will find where it came from. It's that those atoms are missing an electron. It'll find where it came from and release that energy as light. So from light to light, right? Through absorption into the quantum dot. And that's where we see the different colors then appearing, where the small particles that have higher energy waves have light which is of higher energy than the particles which have longer energy waves. And then you see in fluorescence then, this is all using a UV light to excite these single electrons, and then the particles then re-emit the light depending on the size of the particle. So it's very much like if you have a guitar, right? And the guitar strings are the waves creating the sound, and you excite the guitar string by plucking it, right? So the plucking the guitar string is like shining light here, right? You need energy from the outside to create the wave in the cavity, and then you hear the sound of the guitar string. In this case here, we see the wave as the photons coming out, as light coming out. So that's really all you need to know in terms of the quantum mechanics for why these materials are interesting. So when I first encountered quantum dots, I thought, you're seeing quantum mechanics with your eyes. How beautiful is that? That's just amazing, right? And then you can manipulate that quantum mechanics by adding a few atoms more, a few atoms less, and just control that quantum mechanics using chemistry. And I fell in love with it. Okay, so about a year and a half ago or so, I was in Stockholm with these two gentlemen, Lou Bruce and Alexei Ekimov. And let me tell you about how they came about discovering the quantum size effect. So the prize was for the discovery and the synthesis, and their contribution is the discovery part. So Ekimov he was really interested in what gives color to stained glass windows. And it was already known that the red color was due to small gold particles, right? And Faraday had known that back in the late 18th century, and you can see the gold soles in the Cavendish Museum. Small, when you make gold very small, the way that it interacts with light is it scatters red light, right? What about the other colors? So he looked at recipes from the empirical recipes, and if you isolate in those recipes just the elements that you think might provide color, you get rid of all the stuff that's there in order to make the glass easier to process, and you leave behind like cadmium and selenium or copper and chlorine, for instance. So he processed it in different ways. He couldn't access the particles using an electron microscope, but he could use small angle X-ray and was able then to correlate the size, average size given by small angle X-ray with the color that he saw. And he wrote a paper in the Soviet literature, eventually translated, with the first three words, quantum size effect in three-dimensional microscopic semiconductor crystals. Lou Bruce was working at Bell Labs around the same time. He was interested in measuring the kinetics at which these electrons, free electrons, go from a semiconductor to an electrolyte in solution. So he was interested in understanding the kinetics of the electron going through that interface. And in order to get better signal to noise, he needed more surface area, because it's a surface effect, right? And so if you make the particles smaller and smaller and smaller, then your signal should get higher and higher. And there were recipes for making small particles of semiconductors from the Hanglein's work in Germany, and et cetera. Those people were interested in doing radiochemistry with those things at the time. So he used recipes that were generally at room to low temperature, used the cadmium sulfide, under dry ice conditions to make the particles. And he would do the experiment mixing cadmium chloride with hydrogen sulfide, and every time he would see slightly different color, right? And using the spectrometer, and he thought maybe I'm not a very good experimentalist, whatever. But he had access to electron microscope at Bell Labs, and so he was able then to correlate what he was seeing spectroscopically with what the sample was giving him, and was able then to write a paper with the first three words, quantum size effect. This is in the redox potential because he was interested in using the electron to do electrochemistry, photoelectrochemistry. Alexei and Louis didn't know each other. It was the time of the Cold War. There was an iron curtain, between the iron wall between the two countries. And the reason why I think they both came up with the same understanding is because they were surrounded by physicists who were interested in quantum wells, studying quantum wells for the quantum confinement in a quantum well is this two-dimensional film that's very thin, and you have the quantum confinement in one dimension. And that was really becoming important for making lasers and amplifiers for telecommunication. So they were surrounded by this idea of quantum confinement, and that's why they ended up coming up with the right answer. Eventually, Louis wrote a letter to Ekimov. He found the paper and inviting him to say, we should talk, right? And Sasha Efros was part of the team, and Sasha talks about how the KGB found that letter before it actually arrived to Ekimov and Sasha Efros, and they got a visit from the KGB to try to understand why an American scientist would be interested in this topic. What was so important about this? So that was the discovery. So my contribution, along with Chris, my first few students, was to be able to synthesize this. So if you go back, the discovery was in the early 1980s. So there was about 10 years between the discovery and the synthesis, which really became the catalyst for really growing the field. And that's not uncommon. right? You see a discovery. During those 10 years, Lewis built up a group to try to figure out, he knew that you needed better samples. The initial samples were done at fairly low temperature in water. And if you know anything about semiconductors, like binary semiconductors, those are two terrible ideas, right? The surface of a semiconductor, you put it in water, it's going to oxidize. And you've got a nanometer piece of semiconductor, you put it in water, it's going to turn into an oxide pretty quickly, right? If you want to have a crystal, that's a pure crystal, and 2 6s or 3 5s, room temperature is not going to make a good crystal. You've got to anneal it, you've got to go to high temperature. So the ideas of high temperature and getting rid of water and oxygen weren't there yet, right? But in retrospect, those are pretty obvious ideas. But so for about 10 years, they were able to see the effect, do some experiments, but in order to study the physics, to really understand the curiosity-driven question, which is, what happens to matter when you go from the atomic scale to the macroscopic scale? What happens to those properties when you go from an atom that has very specific quantum levels and that behaves completely differently from the bulk materials? What happens in between? How do you build up the collective properties of the solid? Where do they start to happen? Do you need 3 atoms? Do you need 1,000 atoms? And which properties evolve first into the bulk? Right? So those were the questions that really drove the field at the same time. But in order to be able to study those questions, you needed samples. I was a postdoc at Bell Labs, and actually, when I accepted my postdoc, Lewis told me, "Yeah, cat selenide is all done. You're going to be working on 3 5s on gallium arsenide." And so, oh, great. And I came to Bell Labs, and cat selenide was not all done. It's still not done in some ways. And so I was given a project based on cat selenide, which I pursued. And part of that work, accidentally, I was able to take some of the room temperature water-based particles and using organic solvents at reasonably high temperatures, I was able to create, somewhat accidentally, a sample that was much more crystalline than we had ever done before. With the size distribution, it was much better. It was the first time that we actually used a nucleation and growth time of idea to grow the samples. So I made little tiny seeds in the water-based system, and I took those seeds and I put them under nitrogen in this solvent system, and I watched the particles grow. Okay, so nucleation in the water and then growth in the. The problem with this preparation is that it only gave me one size of particles, and it didn't work all the time. And I didn't really understand why it worked. I was not a synthetic inorganic chemist by any means. Mike Steigerwald was the inorganic chemist, and he taught me everything I know about organometallic chemistry. So when I came to MIT, I was going to study all this physics, and the first thing I did was to try to reproduce the work I had done at Bell Labs. And what was sometimes at Bell Labs became never at MIT, and Chris remembers those days well, right? So I came in July of 1990, and for the first 3 months, before my students really came, I accomplished nothing, except spend a lot of money and think, oh my God, this is never going to work. But the wonderful thing about being at a university is you get first-year students, like Chris and Sherry and David Norris and my first set of students, that they still don't know failure, right? And they think you can do anything, right? So you give them a problem and they, yay, right, let's go fix this problem, right? And so this is the fall of 1990 now, and so Chris is starting out, and he's starting to hit his head against the wall, but the joy of being a professor is that every now and then, a lot of the time actually, you get students that are smarter than you, and they have a fresh mind, and you give them just the right input, nucleation and growth, high temperature, and get rid of water, right? And then they just figure it out, right? They run away with it. And so, so that's what happened, right? And so this is Chris as a young man, and this is David Norris as a young man. And they came up with, and Chris came up with this idea of this high temperature, this what is now called the hot injection system. So the precursors are here, and I had learned about some of these precursors from Mike Steigerwald, dimethyl cadmium, a terrible precursor that today we no longer use, but we were a little ignorant at the time. And then a hot solvent, so you take room temperature stable precursors, you inject them into a hot solvent, they crack, they release the atoms that are going to make your quantum dot. And that's the nucleation part. You've separated nucleation and growth in 2 steps, and then it slowly grows in the presence of ligands that protect the surface as it grows. And you control it. And this is a very simple idea, right? It's really simple. But it turns out that simple is sometimes really important. Okay, and so then we wrote a paper. This was my first paper at MIT in 1993, so for 3 years. If you have an assistant professor that doesn't produce any papers in 3 years, you think, this guy's going to fail, right? Something's really wrong. Anyway, this was my first paper, and there's some important words here. It was simple, it was a single reaction, and there was the size selective precipitation that was basically a way of purifying the nanomaterial. Simple and single reaction eventually turned out to be really important for this to become a technology. Because if you make anything, the cost of that thing is proportional to the number of steps, right? If you have a pharmaceutical, if it's a complicated molecule, it's going to be more expensive to make than if it's a single-step object. A car that has a lot of parts is more complicated to make than a simple car. It will cost more money. A semiconductor that has a lot of circuits on it is more expensive than one that has few circuits. So simple and single step, that turned out to be really important for this. And also that turned out really important for other people to be able to use this idea, this concept, right? And then this is chemistry right here. So if you're making a new molecule, you purify your molecule, right? You get rid of all the extraneous stuff. And this was a way that based on polymer literature that Chris read in the basement of the library at MIT. This is basically polymer purification by molecular weight. Okay, so this paper, it turned out, was a really important paper, but not just for quantum dots. It turned out to be really important for the general field of nanomaterials, because it showed that you could create a nanomaterial with a lot of control, and that you could create something that was almost not, I won't say perfect, but that was really well defined, right? And so the field went from creating huge distributions of stuff where you could see effects to really controlling the material at a nanometer size, within tens of atoms, basically. So you could really start to study some really basic physics, really fundamental science. And I think that's really the importance of this work. This was also Chris's first paper in quantum dots. Okay, and this is what it looks like. So you've got the precursors. This is at 300 degrees Celsius, this flask here full of, and then you have the quick injection, and then the nucleation. So this is at high temperature. So these particles are probably, a couple nanometers, less than a couple nanometers in diameter. And then it keeps growing, so that nucleation, then the growth step. And then it gets, we're going to skip 20 minutes here. It's going to turn much darker. So we've skipped about 20 minutes of growth. And you can still take samples out. And you can see then the evolution of the growth of the material, keeping the size largely intact, and based on the ideas from the 1950s of nucleation growth that physical chemist Lemaire had talked about. and then you can turn on the UV light and then see the fluorescence. The fluorescence of these materials, when we first did it, was on the order of 20%-ish. And I was so excited because these looked so bright to me. The reason why they looked so bright is because the samples I had made at Bell Labs had a quantum yield of 0%. So 20% is much bigger than 0%. Right? Then I started to give talks, and I had a colleague in Germany, Horst Weller, and I said, wow, they're so bright. He was also working on quantum dots. 20%, he said, that means that 80% of your sample is crap. The field took that to heart, because now the samples have 100% quantum yield, because really there was nothing intrinsic about the material. So when you have a property that's not optimal, you want to optimize it and make it better. Well, first you have to decide, is there something intrinsic about the material that will prevent me from ever again making this big, right? So you think about the properties of the bonding or whatever, maybe you're making triplets, you're never going to be able to get all your singlets to emit. So there was nothing intrinsic except the surface was where we were losing lights through defects, right? So that interface then became really important. People started to try to understand how to make that interface better. Okay, but what this allowed us to do was to start to do physics experiment. I'm just going to show you one example here of the kind of fairly sophisticated physics experiment that began to teach us about this evolution of atomic properties into bulk systems. This is a low temperature experiment, so these are the room temperature spectra here, from small particles to large particles. This is from Chris's thesis. Marching through the visible here from 400 to 650 nanometers or so. This is about 50 nanometer sized particle. If you take these particles now, cool them down to low temperature, and look at these excited states here. So these are the excited state of the particle in the box. You can think of these things as the harmonics of your sound wave, right? You pluck your string, you hear the fundamental, but a bunch of harmonics. So these are the excited states. And so these are small particles here, and you see the harmonics, the excited states, and they're all sort of spaced in a way that could make sense, and they're all, as you make your cavity larger and larger, the harmonics get closer and closer together. That's what you think of a wave in an empty box, right? But at some point, these harmonics behave strangely, right? Like this one suddenly plateaus out and goes back down. This one plateaus out, and there's this thing here, which spectroscopists, we call that an avoided crossing. It's a quantum mechanical two states that interact with each other that are trying to cross their energies, but they can't because they're interacting with each other. So avoided crossing tells you something really fundamental about your system. In this case here, they tell you that the box is not empty. There are atoms in there, and that electron wave is interacting with the atoms in the box. And that interaction really only starts when the box has a certain size. If it's bigger than a certain size, then you start to see that interaction, and it affects the particular properties. So this is the kind of size-dependent fundamental physics properties that we were interested in. Chris and Sherry also then realized that you could assemble, if your particles were good enough, they could assemble into kinds of crystals. And this is a field that Chris and Sherry are still a big part of. And so if you think of these now quantum dots as having a wave in there, right, and they're beginning to interact, maybe they can interact quantum mechanically with each other, just like atoms in a solid interact quantum mechanically. And that quantum mechanical interaction could give rise to new properties. Right? A solid made up of atoms has properties that are different from the elements that make it up. And when we saw this, the first thing is, okay, now we have a potential of making new materials where the building blocks are now these quantum dots. And this is still a huge field of this nanoparticle community of figuring out how to assemble them together, making binary, ternary materials based on different quantum dots or quantum dots with magnetic materials, etc. Try to give new properties to these supercrystals. You can see the kinds of beautiful SEMs, and you can make them actually pretty large. And this is all work that Sherry did here as a younger person in this photograph, although she looks identical today. And she did back then. unlike some of us. Okay, now, so this is 1993 was this paper. So there was 10 years where not, a lot of work went on, but now we had this synthesis that provided very high quality material. And this idea that, there's nothing intrinsic to keep the quantum yield down, so let's make it bigger. And Steigerwald and myself and Bruce had played with these sorts of core shell particles back when the synthesis was still water-based. But then if you apply these same ideas to these new high-temperature, air-free synthetic ideas, then within a couple years of the 93 work, suddenly, first of all, a community started to build. At the beginning, there was no community. There was just a couple groups, myself, Paul's group at Berkeley, maybe a few groups in Germany, Louis at Bell Labs. But suddenly a community came. Guillaume Sionnet, Philippe started working on this. And then we figured out how to get that interface, the quantum dot inside, to be much more defined by growing another semiconductor, or maybe multiple semiconductors, and then there are organic groups on the surface, creating M&M structures, right? We protect the core, melts in your mouth, not in your hand, right? And that gave rise to these very high quantum yield materials, which today are essentially 100%, plus or minus. And so when you suddenly have all these colors that are now truly efficient, with an absorption spectrum that looks not at all like a dye absorption. A dye absorption would be the mirror image of the fluorescence. And right in the mid-90s was also the discovery of the gallium nitride diode, which emits blue light very efficiently, which has changed our lives in terms of lighting, for instance, with an emission, let's say, around 465 nanometers or so. Then all of us, the community realized, I think we can use this for something. Right? Because now you have a series of materials that you can use a blue light to excite all of the colors at once, parallelized. So the idea of multiplexing fluorescence with one excitation source was in the air. You couldn't do that with dye molecules. With dye molecules, you need multiple laser sources if you want to multiplex. Here you could do it very easily. And because we were chemists, the first thing that came to our mind for applying this was biology. Biology is the closest to chemistry. You use biological molecules, right? And so a bunch of us, essentially at the same time, came up with the idea of trying to make these things compatible with biology, which was actually quite hard because, again, these are semiconductors that in the presence of water want to oxidize. So you've got to protect the surface to make it biological compatible. And so this is 97, 96 when these papers come out, a few years after the 93 paper. Within a year and a half of these papers coming out, Paul Visados and I and Shimon Weiss started a company called, Okay, let me backtrack a little bit. What these core shell particles also allowed us to do was to go and look at the particles one at a time in a microscopy. And this was at the time that single molecule fluorescence microscopy was also coming out. So I was surrounded by people, being very energized by these single molecule spectroscopies. And I thought, quantum dots, that's the perfect material because when you do single molecule spectroscopy, every molecule is the same, right? But quantum dots, even though they're, all roughly the same size, they're all different. This dot has 1,000 atoms, this one has 1,002 atoms. The surface is slightly different. So if you really want to know the physics of these quantum dots, you've got to look at them one at a time. And then you can look at the distribution of the responses, et cetera. So that's what we did within, this is 96. So as soon as we had core shell dots, we started looking at them one at a time. And we discovered, for instance, that they blink. Okay? Today we know how to make that much less. And we go to low temperature, and we see that we can see what are basically vibrations here, right? The line was get much narrow. This is the image. These are the spectra in the line here, and these are vibrations. So we start to learn a lot about the physics of the material, one at a time. We can go time on this axis here, energy on this axis. Look at the light coming out. We see these spectral jumps, which we can then identify as charging of the dots, or charging of the surface and then motion of the electrons on the surface, or when you have very small shifts in the energy here, maybe local charge dynamics or dipole moments that are going like this, changing the Stark effect of the. So you learned a lot of really subtle but really interesting physics along the way. Okay, and today we're still doing single quantum dot applications, but now we're looking at applications in quantum optics for these particles. And the one I'm going to tell you about very briefly is using these quantum dots made out of perovskite materials, fairly large ones, on the order of 20 nanometers, maybe not as quantum confined as the previous ones. So let me tell you just very briefly why they're so interesting and what causes them to have these interesting quantum optic applications. So when you cool down a semiconductor material at low temperature, most semiconductors, the lowest state is spin forbidden, meaning that the light coming out is very slow. The lifetime of that emissive state is microseconds, maybe hundreds of nanoseconds, right? When you cool down these perovskite materials, the lifetime is really fast. It's 200 picoseconds. That's really unique, right? There's no other semiconductor quantum dot that has these really fast lifetimes at low temperature. And if you look at, what's interesting about having a fast lifetime? Well, if you look at this equation here, this is called the T2 star is the dephasing time, right? The intrinsic dephasing time. This comes from, if you've got a two-state system, right? In a solid state, the lower state and the ground state and the excited state may not be very stable relative to each other because there's thermal motion, for instance, right? There's noise. And this T2 star is basically the effective time where these two states stay coherent with respect to each other, where the energy difference is well defined. If we wait a little bit longer, the energy difference becomes less well defined. And from the Heisenberg uncertainty principle, if you're something where the energies, there's a time connected to that, and then there's a time energy uncertainty, right? The time energy uncertainty tells you about the line width. In any case, the full dephasing time is connected to the intrinsic time, connected to this motion, and the radiated lifetime. So if you want to have a line width, which is as narrow as you can, you got to get rid of this term right here, which means you want to have this T2 over 2T1 be equal to 1. You don't want to have, you want the coherence time of these two states to be as long or longer than the lifetime. So how do you do that? Well, you can have a really short lifetime, right? And so we thought, this is great because now we have this really fast, maybe this is slow enough that we're going to be in this situation. And if you're in that situation, called the transform limit, then what happens is that you can have a really interesting effect called the Hong-Ou-Mandel effect, which I'm going to tell you about. But before doing that, you have to be able to create one photon at a time. Okay, you have to be able to excite your particle with a pulse laser and create one photon at a time. How do you see that? This is these correlation experiments. I want to just focus on this peak right here. This peak is basically the probability of two photons coming out together doing the pulse of excitation. And not having a peak here means that you only have one photon coming at a time. Right? So we can make these particles, this system, be extremely clean as a single photon emitters. And then the Hong-Ou-Mandel effect is just a simple experiment. This was, let's say you have two photons, this is a beam splitter, coming together on a beam splitter from different directions. And if they're different colors, then you get a statistical distribution of measured outputs. You can have this one going straight and this one going straight, or reflecting, or one reflecting and the other not. So you have these four possibilities. If you look at the quantum mechanics, the wave-like properties of the photons, they see the entire apparatus, just like my first example. And if these two photons, instead of being different colors, are identical, indistinguishable, so the idea of indistinguishable particles is really fundamental in quantum mechanics, right? So they're indistinguishable. Now suddenly you only have two choices. They're measured together. That's called two-photon coalescence, right? This H1 effect. And that's what you need if you want to do quantum computing with photons. This is called linear optical quantum computing. You can also use it for other quantum sensing sort of applications. And so having a material where the dephasing time is long compared to the radiative time could give you this. And so we did the experiment with this. This is one example. This is the lifetime of the particle. We can make the two photons indistinguishable by coming to the beam splitter together, or we can make them indistinguishable this way, or we can make them distinguishable if one is slightly offset with respect to the other in time. The gray if they're effectively different colors, or we can put labels on them, and the blue is if they are indistinguishable. And the peak that you want to see, this is the data right here. This is about half the size of this gray peak here. That means that 50% of the photon pairs obey this indistinguishability, which means that we can start to really think about using them for these weird quantum optical phenomena. And I'm really excited about it. This is quantum mechanics again, right? I'm super excited. But let me go back to the applications before I got sidetracked. So as I said, we were chemists. We got these beautiful, really bright particles. We can excite them with one color. And biology was the first thing. We created Quantum Dot Corporation in 1998, just a couple years after the creation of these core shell particles. This is an example of the difference between a dye-labeled part of the cell. This is a dead cell on the nucleus here. And you see the photobleaching of the dye, but no photobleaching of the dots. And that was the selling point here. Then we were able to really understand the chemistry of the surface and do much more complicated experiment. This is a multicolor experiment with quantum dots on very rare cells. You can think of this as a stem cell in the bone marrow, trying to, my colleagues at the medical school were trying to understand the microenvironment of these stem cells and what regulates their differentiation. But you have to find them first in vivo rather. And by using quantum dots, you can do a 3-color experiment. And what you're looking for with these cells that upregulate, both receptors simultaneously as opposed to other cells that do not, what you're looking for is the combination of red and green, which means yellow. And when you see these yellow little cells, you found the stem cell. Then you can do experiments and figure out. This is a hero experiment. So the biology, going into the biology, told us that quantum dots were potentially useful, but it was still very hard. And it's a research material, right? It's not going to go into humans, probably because they're made up of semiconductors and nanomaterials. The FDA process is really expensive and really long, and you've got to do all these tox studies. But you can learn some interesting biology. The other thing that we were able to show is that quantum dots and light dye molecules can go into the infrared. And the infrared is less scattering. We were able to make these composite nanoparticles that emit in the shortwave infrared. This is a glioblastoma model. And you can then go look at these single composite particles and track them in time. They're big enough you could see single ones. And then you can see then the difference in flow between healthy tissue and diseased tissue. And you can see here that the flow is really bad at the tumor, and it's not what it should be, and so this allows you to visualize why it's so hard to treat cancer, right? You may have the best drug in the world, but if you can't deliver it to the tumor, it doesn't do any good, right? And so you got to fix this to increase the therapeutic effect of a drug. That was biology. In the 2000s, a few years after the Quantum Dot Corporation was created, Nanosys and QD Vision were eventually created, and the easier applications came to mind. Now, electrical engineers became interested, right? Electrical engineers working on displays, they saw these beautiful colors. Wow, we should be able to make a display out of that. And so those two companies started working in that area. The first product was actually a light bulb. This was the beginning of LED light bulbs. The color was too blue. They were very expensive. And if you slap on a color filter or an emissive color filter to change some of the blue into the red, you could warm it up and have a better looking light bulb. That was fine. This was a QD Vision product. That was fine until the cost of these light bulbs plummeted from $100 to $10 a piece. And then you couldn't make any money by putting that filter. And so that sort of died away. There's still people working on this because the solution is to take the quantum dots and put them directly on the LED. But the LED gets hot, and you've got to figure out how to solve that problem. It's still a problem that I think it can be solved, and there are people working on it, and I think eventually we'll have dots directly on the LED. But the application that really took off was the displays. Blue emitters, green and red emitting dots, so blue LEDs, to create the RGB in a display screen. First company was Sony to use them from QD Vision dots. I still have these televisions at home. They still work. They were over-engineered, but they stopped selling them after 1 year because they were made with cadmium selenide, and there was a public relation problem with having cadmium in a consumer product. Even though it's well encapsulated, it's not going to go into the environment, et cetera. Samsung saw that, and Samsung had the patience and the money to spend many years developing indium phosphide as a replacement to cadmium selenide, something we could not have done in academia because it was too costly, really, to do with graduate students. And you really needed to have the quality control to do things really reproducibly. But they did it, and the first television was this in 2015. And they had the local QLED, which they bought from QD Vision. There's the little Q right here. And that little bar right here cost them about tens of millions of dollars. That's what they bought the company for, is the marketing part of it. The technology, who cares about the technology, right? But marketing, because LG was selling OLED TVs, so OLED, QLED, right? Today, the technology is going to QD OLED, which means you make blue pixelated OLED that are individually addressed, so organic blue pixels. Then you inkjet print on top the QDs, and you have your RGB. And you can make very efficient, very bright displays. They're beautiful. And because you can make them more efficient, you can also make them bigger. And so they use even more energy than the old ones. But they're beautiful. You have applications in solar and in other things. I think I lost. Let me skip. Let me skip this one right here. Okay, lots of applications still. The next display one is going to be electroluminescence. So that's probably going to be in three years or so that you're going to see displays that are pure quantum dots without the blue OLEDs in there. There's night vision type cameras, SWIR cameras. A bunch of small companies are trying to commercialize this. PV in some way or another. And so all of this, took a lot of students from me, but also from the community. I've had about 100-odd students of my career. And within the late 90s, the community started to grow and grow and grow. And Chris had students, and Sherry has students, and all our students had students. And now we have a big family tree. And all of that, we had a reunion. So it's nice to see faces to some of these people here. There it is. We had a reunion. Okay, forgot about the faces. No, here we go. And I want to highlight the funding because the initial innovation part, the discovery of the synthesis, was actually funded by internal money. Right? There was my startup package. I could not have gone to NSF and said, I have this idea. I'm not really sure how I'm going to do it because I'm not a synthetic chemist. But I think I need nucleation and growth and I need high temperature. But beyond that, I really don't know what I'm doing. I would not have gotten money for that, right? So MIT startup and then the foundations, that are willing to give you money with half-baked ideas just based on your promise. And within a few years then, NSF actually very quickly, once we had the proof of concept, NSF was important. These government funding sources were critical to growing from the initial innovation to creating a field, a community. So those were super important to build the science based on that initial innovation. And once you show innovation and an application, then suddenly the companies start going in and giving you money. But this part right here, which we're all very worried about now, if you skip this part right here, you never get to this part right here. Right? You just kill it completely. Okay, thank you, and yeah, thank you for your attention.
There are many questions. We do have a small presentation that we'll make, so we might have to just keep it to one, but do we have any energetic volunteer that might want to ask a question? All right, we'll go to the front.
That was a great talk. In terms of quantum dots now, I guess for biological applications, what is the multiplexing capacity of quantum dots?
Multiplexing for quantum dots? I think it's really, it's something that's underutilized, the multiplexing of quantum dots. And part of the reason why it's underutilized is because there is no good stable commercial source of quantum dots that can be applied for biology. I have a friend in France who developed a way to multiplex using multicolor fluorescence for a diagnostic. He built a little device, and he told me quantum dots would be perfect for this. And in fact, the proof of concept used quantum dots. But he said then we tried to find a source, and every time we bought samples, they were different. And so we had to re-engineer our concept to use dye molecules. And that really breaks my heart. So, it's a great material for biology, but without a stable commercial source. And the problem is that, those patents are long expired. Thermo Fisher sells quantum dots based on a technology from 2000. They did not innovate since then, and the market is too small. So, and the market can't grow until there's a good source. So you have a chicken and the egg sort of thing.
Very good. Well, thank you, folks. We have a presentation. BJ will take over from here.
Thank you very much for this amazing talk. It's an honor to share the stage with you. And on behalf of all of us, we want to present to you a small token of our appreciation and to congratulate you for the Nobel and for winning the Harold Berger Award. So the acknowledgement says, the Harold Berger Award presented to Moungi Bawendi for groundbreaking advances in the synthesis and applications of semiconductor nanocrystals, March 19th, 2025, School of Engineering Applied Science, University of Pennsylvania. Thank you.
Thank you.